My dear students, welcome to session 10 Fluid Mechanics. Today we will discuss the hydrostatic force on curved surface. Yesterday we have taken problem on plane surface. Hope you remember, we have taken a problem on a plane surface with a submergence in the horizontal direction, and we have obtained the hydrostatic force and center of pressure for the horizontal position of the plane by using the formula gamma W into area of the plate into the depth from the water level. So, formula is F is equal to gamma W A H bar. We have taken a problem on an inclined plate and we have taken a problem with a vertical plate to determine the hydrostatic force acting, which is the center of pressure acting slightly below the centroid. Today we will continue the discussion. The module 2, the first part is hydrostatic forces on surface. You can see a curved gate here shown in the diagram in a canal. We would like to know what is the force required to lift this radial gate or a curved gate when what is required downstream. The learning outcome is the student will learn to determine the hydrostatic force on submerged plane and curved surface and its application. We will go with the problems again. Before I start, I would like to take on one more problem. Total pressure acting on an immersed surface, the formula is P is equal to or F is equal to gamma W into G into HC, which is 1000 into 9.81 into the depth of the centroid from the free surface. Is it okay? Exactly like this, free surface and depth. Okay. The formula for the center of pressure where this force will be acting, that is called center of pressure. That is called center of pressure. This center of pressure can be obtained by using the equation h bar plus Ig sin square theta divided by area of the plate, which is say L into B, into h bar, which is the depth of the centroid from the free surface. This one G I have shown in the diagram, correct? And as far as the angle theta is concerned, if it is horizontal, yesterday we saw it is going to be 0. So, H center of pressure will become same H bar. It means the center of pressure and the centroid will be acting at the same point. The whole force will be acting at the same point. Is it okay? In case of inclination with an angle theta, the formula is HCP is equal to H bar moment of inertia Ig into sin square theta divided by area of the plate, which is the length by breadth, and in case of theta is equal to 90 degree, which is exactly like this, which is a 90 degree, the angle is 90 degree now. So, formula becomes HCP is equal to H bar plus Ig sin square 90 by A into H bar. Sin square 90 is 1, so formula becomes H bar plus Ig divided by A into H bar. So, this is the way you can understand the center of pressure, which is slightly below the centroid in case of a vertical or an inclined surface. So, before we complete this plane surface problem and move on to the curved one, I would like to take one more interesting problem, which is a hollow circular plate. You can see here it is a hollow circular plate and it is inclined at some angle. I would like to know where is the force going to act, where is the total force, the center of pressure is going to act on this hollow circular plate. Okay, let us read the problem very carefully. A circular plate with a concentric hole is immersed in water in such a way that its greatest and least depth below water surface are 5 meter, which is you can see here, this is 5 meter and 2 meter respectively. On the upper edge is 2 meter. It means if you say this is the plate and it's something like this. So this value is 2 meter and from here to here it's 5 meter. Is it okay? Have you understood this? Yeah. Determine the total pressure on the plate and locate if its diameter of the hole are 4 meter and 2 meter respectively. It means this to this end, the diameter is from here to here, it's 4 meter. In the hollow, it is 2 meter. Is it okay? So mind it well, it's not a solid plate. If it is a solid plate, the area becomes pi r square directly. Now it's a hollow plate. So we start the problem very carefully. For a hollow plate like this, the density of water is given as 1000 kg per meter cube. G value we are going to take 9.81 and the area of the plate, which is a hollow circular plate, you can see it will be pi by 4 capital D square minus pi by 4 small d square. Okay, substitute in the formula. Pi by 4 d square is 4 square and other diameter is 2 meter, we say 2 square. So we calculate the area as 9.424. Is it okay? So be careful, it is not a solid plate, it's a hollow plate. So the area of the hollow circular plate is pi by 4 d square capital D bigger D 4 meter, which is shown in the diagram also, and the small d you can see which is 2 meter, we are going to calculate as per the formula, right? Now H centroid, I would like to know what is the centroid of the figure. Centroid of the figure, yesterday I have given you a hint, you remember? Whatever the least height is there 2 meter, whatever is the greater height is there 5 meter, take the average of the two. Repeat, in this case the least height is 2 and greater height is 5, take the mean of the two. What is that? 5 plus 2 divided by 2, as I have shown in the slide also. You can see 5 plus 2 by 2, it becomes 3.5. Okay. So we are knowing the centroid, we are knowing the area. Now I can calculate the force now. How I can calculate? Come to the bottom blue part. F is equal to gamma W into A into HC. Gamma W of water is 9810 into area 9.424. Use your calculator, into HC, which is 3.5. As I mentioned, take the least height, take the greater height, 5 plus 2 divided by 2, it's 3.5. We can see the value is obtained as 323.573 kilonewtons. I have divided that value by 1000. No need to surprise, right? So the total force I know now. What is the force now? 323.573. Now question arises where it acts, but before that I need to calculate what is the inclination of the plate. You can see the plan is shown in the diagram, exactly same thing which is shown to you in the figure also. Now theta I would like to calculate. The theta, you can see here the value is 5 meter and least height is 2 meter. So what is this height, my dear friends? It is with 5 minus 2, what is the value? 3 meter drop. You can see sin theta is 3 meter drop. What is the inclination here? The maximum diameter or the higher diameter, the value is 4 meter. It is mentioned here also. I think I have shown by an arrow, if you can remember. You can see here 4 meter is the 4 meter. So sin theta is perpendicular upon hypotenuse. Perpendicular is 3. You can see how this 3 has come. Maximum is 5 minus 2, that is 3. So it is going to be 3 by 4. Sin theta is equal to 0.75. Use your calculator and work out what is the angle. The angle will come out as 48.6 degree. Is it okay? So hopefully I have explained you how to calculate the inclination. How we have calculated? The drop is 5 minus 2, 3. Hypotenuse is 4, 3 by 4. Sin theta is equal to 3, which is the drop, divided by 4, which is the maximum diameter, which is 4 meter, and the value is 0.75, and theta is 48.6. Is it okay? Now let us go to the next slide. In this slide you will find out, we would like to know what is the moment of inertia. You may be thinking, why I am talking? We need to calculate the center of pressure. The formula which I have given you is HCP is equal to, cursor is there, is equal to HC, which is 3.5, moment of inertia, which I will calculate, sine square theta, sine square 48.6, we recently got theta, you remember the previous slide, here 48.6. So come back, area 9.424, HC 3.5. So my dear students, we need to calculate the moment of inertia of a hollow circular plate. What is the formula? If it is a solid plate, it is pi by 4 r to power 4 minus r4. What is capital R? Bigger radius. What is small r? Smaller radius. Go back to this particular point. The r is equal to d by 2. 4 by 2 will give 2 meter. Small r, this hole is 2 meter. So r is equal to 2 by 2 is 1 meter. I hope you understand. This is 4, radius becomes 2, this hole is 2, half will become 1 meter. Please calculate the moment of inertia as per the formula pi by 4 r to power 4 minus r to power 4. In some of the books or some of the notes you will find pi d4 minus small d4 by 64, both are same. The value will come same as 11.78. Is it okay? So substitute the value pi by 4, 2 to power 4, I think you can calculate 2 to power 4, right, minus 1 divided by 4. So if you calculate, the amount of inertia is known, HC value is 3.5. You remember how the maximum drop was 5 meter, minimum was 2. So take the average of the 2. I told you the shortcut. Directly you get 3.5. It is the depth of the centroid, from the top plate. Is it okay? This is the point C here in my finger. Our water level is here, correct? So we calculate exactly. If you see, figure is like this, from here to here, the value is 3.5. Substitute, you get center of pressure 20 centimeter away, the value is 3.7. It means if you see from the top, if you say is inclination, I will just show you like this only. This value is 3.5, your centroid value for the plate, and center of pressure is slightly going down. It is going here 20 centimeter downwards as compared to centroid. Are you getting it? See, it is an inclined plate, inclined with a 48 degree. This value, which is the centroid, is exactly at the center. This height from the top is 3.5. You can see in the formula HC, and the 3.7 is the slight dip here by 20 centimeter, which is the center of pressure. So this is the way we have solved the problem with all the three kinds of problem, including yesterday I have done for a rectangular, I have done for the triangular, and yesterday also I have done for circular, and today I have taken a hollow plate. So hopefully you have understood how to calculate the total force, total hydrostatic force, and the location of its center of pressure. Is it okay? Let us go to the next slide. Now we go to the curved plates. Curved plate, as I mentioned yesterday also in the beginning of my lecture, that a curved surface will have two components. One will be the horizontal and other will be the vertical. Is it okay? So the horizontal component will act through the center of pressure, not the centroid of the projected area. Projected area I will explain you on the board. Vertical component will be the weight of the system from B to C, C to this point, and back to B. So this much weight we need to calculate. What is the weight? Weight is nothing but the gamma W into volume. Gamma W into volume. What is the volume? You can see here, this is a rectangle and this is a 1/4 of a circle. Is it okay? You can see same thing here also into the length. So the length will be given to the U. What is the length of the gate? For example, if my hand is curved, so this is the length of the gate. Is it okay? Or if I take this cylinder, this particular tumbler as a submerged here. So this will be the portion and this one will be the length for you, that is the length. Is it okay? So we will be seeing how to project it. So one thing is very clear, in the curved surface we have got two components. One is the horizontal and one is the vertical. Horizontal is nothing but the horizontal force, same formula, but only is the projected area. I will talk about that, but formula remains the same. Gamma W into A projected into HC bar. What is HC bar? It will be the, you can say, if this tumbler is there, center of the centroid will be here. Whatever depth is having HC bar, that will be calculating. Is it okay? So with that we will understand what is this projected area, but before that I will go to the next slide. Now you can see there are two components. One is the horizontal component and one is the vertical component. If you take the vector sum of the both, it will be F horizontal square plus F vertical square will be the total resultant force. It means if this is my hand is a curved surface, in that case there will be a horizontal force and there will be a vertical force, but the resultant force will be perpendicular to this surface. You remember in the initial slides I told the pressure on any system or any surface will be always acting perpendicular to it. If it is inclined like this, always this will be always 90 degree. Suppose if it is a vertical, it becomes horizontal. If it is a horizontal, it becomes vertical. If it is an incline like this, it will be perpendicular to this. Similarly, for the curved surface which I am showing maybe by a tumbler here, okay, it will be always perpendicular to that. So it will be perpendicular to that, or my hand, you can see here, it will be perpendicular to this. So that value is your F, which is nothing but vertical component and the sum of the horizontal component. The formula is in front of you. F is equal to FH square plus FV square. Is it okay? Now tan theta we can calculate, same formula, FV by FH. So now we need to know how this projected area concept is going to work. But before that I conclude here. On a curved surface it will be having two components, one is the horizontal and other one is the vertical. The theta angle is obtained by tan theta is equal to FV by FH, that is given in the formula theta is equal to tan inverse FV by FH. The position of F is the point of intersection of the horizontal line of action of FH and the vertical line of action. For example, if this is the vertical line, my hand, and if this is horizontal, so resultant will pass somewhere through this point. Repeat, it is the horizontal point, horizontal force acting here, vertical force exactly say the downward direction, so it is going to act through this point. Is it right? So it will be at intersection point, theta can be calculated based on this formula tan inverse FV by FH. Is it okay? Now before we jump to the problems of the curved surface, let us see what is this projected area which I am talking. I will go back to the slide. Projected area, you can see it is projected on a vertical plane. Can you see here? This is your AB. I am projecting this A to A dash. Let us try to understand what is that. Let us see on the board what is horizontal projection. What is horizontal projection for a curved surface? Assuming that this is a cylinder which water is available up to this point, I want to calculate the projected area. You can see this face is basically a circular face, right, or curved face, right, but I am projecting it to a equivalent rectangle. Again I repeat, you can see it is a cylinder of having diameter d, having a length L. It will become an equivalent projection. This d I will take as a vertical, side, and this length will be as it is d into L. It means though it looks like a curved surface exactly like my hand, right, like this, I will make it equal to this length, okay, into the length perpendicular to it. Means this side, whatever the length is there, means this portion will be the length. So this is your D, you can see, and this is your length, right? So projection is like this. So a circular area of this becomes a rectangular projection. Is it okay? Let us see one more case. Quarter of a circle, I am showing you the second one here, quarter of a circle. Assume that this depth is 2 meter, the radius is 2 meter, and this is a curved surface. Assume the water is here. I would like to know what is the horizontal projection for this. It could be like exactly my hand, right, over which water is there. Here water is there, okay. I would like to know what is the projection. Mind it well, I am projecting now for you. From this point, say A, I will put a dash. This point B, it is as it is B dash. Repeat, this is here A and this is here B. Projection as it is A dash. B to B dash. What is the distance? The distance is the radius, which I have shown here as 2 meter. This becomes 2 meter. What is the length? You can see perpendicular, exactly like my hand. Can you see this portion of my hand? That is your length. This is your length, which is actually equal to 1 meter. I showed. It means this portion is 1 meter. If you ask me in a tumbler way, it is going to be like this. Okay. So we can see here exactly the length is perpendicular to that. Is it okay? So we have understood what is the projected area. Projected area for a quarter circle will be equal to the radius into the length perpendicular to the plane. Length perpendicular to the plane, not this way, this way. Is it okay? So we are looking like this. I think you can see my hand here, no? Right. So this is actually this portion R. This is the depth, or we can say R. Perpendicular to this is my hand, exactly like this. I am putting it flat. So this is your length, right? So that is actually the projected area. We will apply this concept to all our problems today, right? Let us take the first problem. Yeah, my dear friends, you should be ready by this time. We are going to start the problem on a curved surface with this statement. A curved sluice gate, of diameter 3 meter, maybe you can say this is exactly the 3 meter, okay, and water is on this side. Water is on this side. So your length is this side, correct, and 1.5 meter long cylinder. So my dear friends, this diameter becomes 3 and this length becomes 1.5. Repeat, it is exactly, okay, you may be thinking why this is hollow. No hollow, like this only. It is a cylinder of 3 meter diameter. What is the length? What is the length? 1.5 meter. Long cylinder lies as shown in the figure, holding back oil of relative density 0.8. If the cylinder has a mass of 2250 kg, find the reaction at A and reaction at B. Can you read the statement? Yes. The question is asking you what is the reaction at the point A. You can see here A, and at the point B. Done. Now this cylinder, which is having a oil on the this side of 3 meter, of length 1.5 meter. You are right, 1.5 meter. First of all, what is the diameter? 3. What will be the HC? What will be the HC? 3 by 2. So HC is 1.5 because centroid will be here. This is your 3 meter, this length, this diameter, half of that will be centroid. So HC we got to 1.5. What is the diameter? 3. Length perpendicular to the board is 1.5. Specific gravity, which we say relative density, which is the ratio of density of oil divided by density of water, is 0.8, and fortunately he has given you mass of the cylinder as 2250 kg. Is it okay? Let us go ahead. Now the reaction at A at this point will be equal to horizontal component of hydrostatic force. whatever the force is there. For example, if this is the cylinder 3 meter, hydrostatic force is here, like in this direction, Fh. So reaction at A will be equal to that. So we can say Ra is equal to Fh. Is it okay? I repeat, this is a cylinder. In this side oil is there. This oil is trying to push this towards your left, my right. Okay, this is the hydrostatic force Fh, and this is the reaction Ra. So Fh is equal to Ra. Similarly, Rb very interesting. Now this cylinder has got its own weight. It's not weightless. This tumbler has got weight, no. So the weight will be acting downwards. There will be a uplift force Fv because of this oil here, which you are seeing here. So it is going to be lifting upwards. So W is acting downwards, Fv is acting upwards. What is the net weight? It is actually Rb. So Rb is equal to W minus Fv. Correct? Correct? So now we need to calculate one by one the reaction at A and the reaction at B for this interesting problem. Let us see. Now I will go slightly more equation wise. Length 1.5, area projected. I think I already taught you. What is the area projected? Area projected will be 3 meter into 1.5. Correct? Exactly. In this case, the length is 1.5 meter and this is your 3 meter. So what will be the area? 4.5 meter square. 1.5 meter and this value is 3 meter. As I explained to you, the portion which you are seeing, it is going to be converted as a rectangle. The length of the cylinder is 1.5. So 3 into 1.5 is the area projected. Let us go back and continue our calculation. Now we can see the gamma oil, which is 0.8 into 9810, which is the specific weight of water. Please calculate in your calculator also, you will get 7848. Now one more thing which you can see, which we have not encountered earlier, is the weight. Fv, as I told you, the mass, that is okay. The weight is nothing but the mass into g. So weight of sluice gate W, which is acting downwards, as shown here also, W is equal to m into g. Mass is 2250 and acceleration due to gravity is 9.8. So please calculate the weight. Horizontal component, we will apply the formula gamma A projected into Hc. Gamma oil into A projected into Hc. Right? So you can see the values are ready for you. 7848 into area projected 4.5 into 1.5. So if you calculate, the reaction A is going to come in front of you. Please calculate, you will get 52.974 kilonewtons. Is it okay? So this is your Fh, right? Now the upward vertical component. Now we would like to know what is the upward component, which is Rb. Fv is equal to weight of the curve CdB. Whatever this weight is there, we need to calculate CdB. Mind it well, the oil is only on one side. The oil is only on one side. So I will take this portion only, half of the circle, which is a semicircle. What is the semicircle? Which is semicircle is nothing but pi r square by 2. What is the diameter I have given to you? Total 3 meter. So how to calculate the area? Pi into 1.5 square by 2, right? So we can calculate the area as pi into 1.5 square by 2 into the Hc volume. 1.5 is the length I have mentioned here. This length, as I mentioned, is 1.5. So area weight of the curve is equal to specific weight of the oil, which is 7848. Volume of curve CdB converts to area of the CdB, which is half of the circle, pi r square by 2. Length of the cylinder, which is 1.5. You calculate Fv. But now we need to know what is Rb. Rb is W minus FV. What is W? W we already got the value as 22,050. You can see minus FV we have done and converted to kilonewtons. So we got a RA of 52.974 in this direction and RB up downward direction of 19.56. Is it okay? So the net upward thrust we can calculate, and in this question in which we have understood how to calculate the projected area, which is going to be a equivalent rectangle into the length whatever we are giving 1.5 meter in this case, and calculate the hydrostatic force by the formula gamma oil into A projected into HC 7848 into 4.5 into 1.5. Is it okay? And vertical will be the weight of the CDB and the weight. So W minus FV we can calculate and get the answer. Is it okay? Hopefully you understood. Let's take the next problem. This problem is also very interesting, as I showed the diagram here also. You can see there is a curved portion. I would like to utilize this concept in this particular problem. Is it okay? That is the reason I have given R equal to 2 meter and length equal to 1 meter. Let's read the question. Find the resultant force. You can see the cursor. Find the resultant force in magnitude and location on a 1 meter wide section of the circular arc. So 1 meter means the length is given as 1 meter. No doubt. You can see this particular has got a vertical, here concrete kind of a thing is there, concrete base is there, and there is only a curved gate exactly like my hand, or which I shown the diagram there, right. The height of the water here is 3 meter, here the radius is 2 meter, here it is 2 meter. Is it okay? Same radius. So HC, we need to calculate HC for hydrostatic pressure in the FH direction, in this direction. What is that? You can see from the top level, from here to here I travel, it is 3 meter. From here to here I travel, it is 2 by 2. You can see exactly 2 by 2. So HC is 4 meter. Is it okay? Let me repeat. The HC is the centroid of the pressure of the gate, centroid of the gate from the free water surface. Centroid of the gate, this total curved distance is 2 meter. Half of this 2 by 2 is 1, and from this point to this point it is 1 now, and from here you can see we are travelling 3. So HC becomes 4 meter. Is it okay? Now we can calculate the hydrostatic force. Now hydrostatic force, you can see same formula, FH is equal to gamma W into area. Area, as I mentioned, it is a projected area. We will go back. Here you can see it is 2 meter. Projected area, the length is 1 meter. So this depth is 2, which is actually equal to the radius, and the length is 1 meter, which is given in the question. You can see the question also 1 meter wide. So the area becomes R into L. R into L, it becomes 2 meter square. So we can see the same thing here also. 2 meter is a curved area, but it is going to be projected in the form of a rectangle. So 2 into 1 meter wide, you can see it's given in the statement. Take care of that. In case in examination or in any competitive exam, if the width is not given or length is not given, you can take 1 meter. Make a note of it. If the data is not given, you can assume it is going to be 1 meter and calculate the problem. Is it okay? Let's continue our discussion. FH is equal to 9810 into 2 into 1, which is the projection. I think you can see projection I have shown here, 2 by 1. This is 2 meter and this B is 1, which is written here. Is it okay? Yeah. Into the HC, which is nothing but 3 plus 2 by 2, 3 plus 2 by 2, and the value is 78.48 kilonewtons. As far as the moment of inertia is concerned, again depth cube will be there. So B d cube by 12, you can 2 cube divided by 12, that will be 667, and calculate the center of pressure by the same formula. Theta is no doubt 90, HC is 4, IC is 0.667 divided by the area of the curved surface, which is 2 into 1, you remember, into 4, and we calculate the center of pressure as 4.083. 4.083. It means from this point centroid is at 4 meter, no doubt, but we are having the center of pressure at 4.083, very slightly difference. 4 meter is here, slightly 8 mm. Okay. Now the vertical component. Now so far we have not talked about the vertical component. We have talked about only the FH. What is your vertical component? You know very well. The vertical component will be the weight of the water over this portion. Sorry. Weight of the water on this portion. Exactly, if you see this particular shape, from here to here it looks like a rectangle. From here to here it is a quarter circle. I have mentioned W1 and W2. Okay. What is your vertical component? It is the weight held over this particular portion, whatever the total weight or volume is there. Definitely we are going to calculate the vertical component of the force, hydrostatic force, based on weight 1 rectangle plus weight 2 semi quarter circle, right. Gamma W, you can always calculate the specific weight into volume. So volume of this particular pressure prism, volume of this pressure prism is nothing but area 1 plus area 2 into the length. Length, as you mentioned, is given as 1 meter. So let us go there. W1 plus W2 becomes gamma W into length. Area 1, what is area 1, my dear friends? You can see in the diagram, it is a rectangle. What is the value? 3 into 2, you can see here, rectangle 3 into 2, correct? Correct. Next, the quarter circle, what is the radius? 2, so pi r square by 4, very important. This is the way you have to analyze the problem. This problem, which has got two component, horizontal and the vertical. Vertical is the weight of the water above that circular, or you can say curved portion. It is going to split into two. One is the curved portion, one is the rectangle. You can see that in the slide, and once you calculate, you get the total weight as 89.679 kilonewtons. Is it okay? Now taking moment about the A, because this W1 will be acting at 2 by 2 here, and this W2 will be acting at 4r by 3 pi. You remember the formula I have given for centroid for a semicircular or quarter circle, 4r by 3 pi. What is the value? 4 into 2, radius is 2 meter, 3 pi is a constant. So multiply by this weight, which is 30819 with this value, and this value 1 meter into the rectangular equal to the total weight, which is the 58,860 plus 30,819, 89.679. If you calculate, you get the resultant location also where it is acting, which is very much required for us, because we need to calculate where the resultant vertical force is acting. Force of 89.679 kN is acting from the point A. From the point A. So I know the value now. Okay, let us go ahead. Now we would like to know the resultant force. As I mentioned to you earlier also, it has got a horizontal component, it has got a vertical component, so resultant will be there. What is that resultant? It will be square of FH square plus FV square, that you will get the resultant value, and the angle is calculated based on theta is equal to tan inverse FV by FH. So if you do that, you get R is equal to 119.2. You can calculate or verify with your calculator, and the theta is 48.81. It means this angle is 48.81. So it is very important. You can see I have shown here, this point is acting here at 0.948 from the point A, and from this location it is 4.083 center of pressure, which is acting from the free location for FH. So this question is giving you an idea how to calculate the FH and FV for a curved plate. Is it okay? Let us take next problem. Next problem, find the magnitude and the line of action of the hydrostatic force. Exactly a similar problem, but slightly dimensions are different. Now in this case, you can see here FV is shown the vertical, same thing as the previous problem. FH will be acting here. So I need not explain this again, because more or less the problem is same. You agree with me? Where is HC? HC will be 4 plus this distance, which is 2 meter. You can see exactly at 5 meter, and we can calculate 2 into the length is not given, we will take 1 meter. So same problem with variation of values. So I will skip this and go to the next problem. Next problem is a very interesting problem. It is a gate. I think I will show you the gate first. This is the gate, same gate which I showed in the starting slide. Yeah, this one. Can you see this one? It is exactly like this. So it is sitting on that. 3/4 of it is on the top open and 1/4 is under water. So we are going to lift it like this. I repeat, 3/4 is on the top and 1/4 only is sitting here. So I am going to lift it like this. I would like to know what is the force required to lift this gate. Okay, so let us take a very practical problem. In this case, let us read the statement. We call it tainter gates. You can see here the length of a tainter gate perpendicular to paper is 0.5 meter. So he is giving you L is equal to 0.5. Exactly, my hand width is 0.5. Find the total horizontal thrust of water on gate, total vertical component of water pressure against the gate, resultant water pressure on gate and its inclination with horizontal. Now you can see the length is 0.5, AD is equal to BC, which is AD is here, which is equal to BC here, projection, which is actually equal to 3 meter. So indirectly you can say the radius portion of the gate which I showed here is 3 meter now. So this 3 meter into the length which is now 0.5. Repeat again, the area will be now, length is 3 meter, or radius is 3 meter, but this length is only 0.5. So the area will be, you can calculate 3 into 0.5. Let us go to the further. Gamma W is water is held on the left hand side of this one, exactly like this one, my hand, right. This side you have this one. I want to lift this gate. Hinge is there, you can see about which it is going to rotate. The radius is given as 60, this angle is given as 30. Okay, let us take one by one. The total horizontal thrust of water on gate, FH will be equal to gamma W AHC. My dear friends, you know very well, if this radius is 3 meter, okay, where will be the centroid? Half of this, which is going to be 1.5 or 3 by 2. So go back to formula. 9.81 into the area, 3 into 5.5 into 3 by 2. We calculate, we get the FH value. Where is the location? Same formula. HCP is equal to HC Ig sin square theta AHC. It is a vertically immersed gate. Theta is again 90. Ig is 0.5 into 3 cube. 0.5 is the width, you remember. 3 cube is the depth. I always told you BD cube by 12. D stands for depth. So 0.5 is the length into D cube. 3 cube by 12 is the Ig, and sin square 90 divided by the area, which is 3 into 0.5, which I explained to you in the projection. This is the 3 which you are seeing. This is the 3, this portion, and this length is 0.5. So if you calculate that value, it is going to be 3 into 0.5 into HC is again 1.5. So if you calculate, you will find the center of pressure is at 2.0. Now we got the hydrostatic pressure 2, and we got also the center of pressure. Now let us see what is the vertical force. Vertical force in this case, interestingly, will be upward force, FV, upward. We are neglecting the weight of the gate, and now we can see FV is equal to gamma W into area ABC, which is here, area ABC, into the length. Length, as you know, is 0.5. Area ABC, you can see here, the upward thrust area ABC is area AOC minus triangle OBC. Once you calculate, you will get this remaining portion over which the water is acting. For example, if this is my hand and water is acting only on this portion, not in the hollow. So, we are going to calculate that value based on the triangle property. Area AOC, area AOC means curved portion minus triangle OBC. What is this actually? Area ABC pi r square by 12. You may be thinking how we got this. Pi r square by 12 is obtained because the angle at the tenter gate is 30 degree. If it is total 360 degree, the area would have been pi r square. I repeat, r is 6, no doubt. R is 6 now. So, pi r square for the whole circular area, but it is only 30 degree. So, pi r square by 12 minus half OB into BC, which is the triangle OBC. So, if you calculate, we can subtract that value and get the value as 1.636. So, this pi r square 12 has come from where? 360 degree is the total, 30 degree is there. So, 30 by 360 is 12. So, pi r square is the whole area. You divide by 12, you will get the pi r square by 12 of the sector area which we are looking from this point O to A to C in a circular fashion, minus the triangle area ABC, which is half OB into OC. So, we get this value. So, once you substitute the value gamma W into area ABC into length, you will get then upward force so and so. Theta is equal to tan inverse Fv by Fh, which is Fh plus Fv square. So, the total reaction force on this gate is 23.48 kilonewton and angle is 20 degree. Okay. Now, we have one more thing, log gate. You may think, what is this log gate? I will just show you. Suppose you assume that this is a book. Okay. If I open the book, how it will be? It will be like this. A book. Okay. A book like this. I am going to open it. This is called a lock gate, right? You can see the diagram also. It is going to open this way and this way. We need to pull it to open it. Exactly, it is like my hand I am showing you here. It is going to open like this, correct? So, one side you have high water, you can see H1 here, and one side you have low water, we call H2. So, the width of the canal is very important, the length of the gate is very important, and the angle is also equally important. So, we will calculate the angle 180 minus theta by 2, we get the gate angle alpha. 180 minus theta, whatever theta, this theta may be 120. So, it becomes 180 minus 120 divided by 2. So, 60 by 2 becomes 30 degree. So, this is the angle here, and with that we would like to calculate what is the force. Okay. Before I go, I would like to take a small problem. You can see here 2 log gates of 7.5 meter are provided in a canal of 16 meter width, meeting at an angle of 120 degree. So, you calculate alpha here 180 minus 120 by 2. Each gate we can calculate based on the half of this 16 by 2 and 8 by cos alpha. The area is 5 into 9.24. We are going to calculate the area. The force P is calculated by same formula, gamma W area, instead of HC it becomes H by 2. The value of H is 7.5 meter, which is given here. Okay, and canal width is 16 meter, which is given here. You can see we can calculate the width of the gate each, and here we get the value of force here. Now, we go to very important part, gravity dam. This I give my source to NPTEL site. A gravity dam is this much. You can see here this much is the gravity dam. Can you see here? We would like to know what are the forces acting on this gravity dam. The forces which are acting, first one, no doubt, it is the water pressure which is acting on this side, hydrostatic force like this, gamma A into Hc bar. Okay. It has got uplift pressure. You can see here from the seepage there will be uplift pressure, there could be a earthquake pressure, there could be a silt pressure which is here on this side, right, and there could be a wave pressure because of the water, and if there is a ice formation there could be a ice pressure also. So mind it well, in a gravity dam we can have pressures like water pressure, it could be a uplift pressure and earthquake pressure, silt pressure, wave pressure and ice pressure, and this particular diagram shows you a typical hydrostatic distribution, lift and here downstream pressure, and this is the gravity. The whole dam is going to resist all these forces, water, uplift, earthquake, silt, wave, ice, only by weight. That is the name gravity dam has come. The gravity dam resists the force, all the forces, uplift, wave pressure, uplift, earthquake, water, everything by its own weight, which we call the weight here, and the resultant should pass through middle third of this. Whatever the B value is here, B by 2 we can take B by 6 this side and B by 6. So resultant should pass through that, so that the dam will not fail. Is it okay? So in this case we have completed the module 2A fully. We are going to start the next lecture with the kinematics of flow. Mind it, my friends, don't miss the class. We are going to start the flow. Now fluid will be flowing. I would like to know what is the velocity, I would like to know what is the acceleration, etc., etc. So thank you for your kind attention. Thank you very much.